Hi everyone, this is the last video in the molecular spectroscopy section of Chem 2922. So we've come to the end and our final topic is gas analysis. We are going to briefly discuss using some of the techniques that we've been studying, such as infrared and Raman and UV-Vis, to analyze various gas samples such as exhaust plumes and the atmosphere. Well, if you need a motivation for why gas analysis is important, here's one. Carbon dioxide. It's present in the atmosphere as a gas, levels of hundreds of parts per million, and over the last century and a bit, it's increased quite a lot. And that's because we are burning lots of fuels that contain carbon. And when carbon burns, it makes carbon dioxide. So, keeping track of the level of carbon dioxide in the atmosphere is very important. And so, accurate measurement is critical here to inform the political discussion. Sometimes that information is not acted on, but, as analytical scientists, all we can do is make sure that our measurements are as good as they can be. There is an observatory in Hawaii which spends a lot of its time measuring very accurately and precisely the amount of CO2 in the air. Now, I have to say that would be a pretty good job to have. Get to do science, get to work on an important problem, get to live in Hawaii. Not bad. Here's one way to do gas analysis using infrared. You can do it either by emission or by absorption. So we've been talking a lot about doing infrared absorption, and that's the example we've got over here on the right. So a little energy diagram there showing some infrared being absorbed, exciting a vibration in the molecule, and we get an infrared absorption spectrum. But you can also do infrared spectroscopy and analysis of gases directly by emission. So sometimes vibrationally excited molecules can relax by emitting packets of infrared-sized energy. Infrared emission can be conveniently monitored from a distance. So you can put a detector on the ground some distance away, or you can put one in an airborne device and measure from afar that way. So the key point is that it requires a hot sample so that the gas that's being produced has sufficient molecules that are vibrationally excited. They are hot, and that you then get infrared emission from them. So something like out of a hot exhaust plume from a factory, from the back of a rocket or plane, or from a car. And here's a little factoid for you. An FTIR spectrometer actually followed Concorde on its first flights to monitor the hot emissions being produced by Concorde. This little picture here is a ray diagram of what's in a Cassegrain telescope. And so by using optics which are coated to reflect infrared radiation, a setup such as this can get quite high collection and detection at the focal point there by this folded back light path. And that means that you can have a telescope, let's say, mounted over here and detecting what's being emitted from this hot gas plume, and our observer over here watching or studying that, monitoring from afar what's coming out of that factory. doing infrared gas absorption faces one big challenge. When working with gases, and especially gases that are at low pressure, such as up in the atmosphere, the concentration is very low. So you don't have much sample, so there's not much absorption going on. One simple way around this is to use a long path length, and this picture here has some nice gas cells, which you can also increase the pressure, have a long path length, and that's great for preparing a sample in the lab. But out in the field, direct monitoring, you need to be a little bit more creative. So samples can be collected out in the field. These people have gone to some fairly remote places to collect atmospheric samples, and by using these fancy balloons, they're getting samples from quite high up in the atmosphere. So they collect a large amount of sample. The volume of that balloon's pretty decent, and that can be taken back to the lab and put under pressure and introduced into one of those glass chambers that we saw before and studied at leisure in the lab. However, if you want to do your measurements out in the field, you have to try something else. So here's a really nice, quite creative solution. This is ALIAS, the Aircraft Laser Infrared Absorption Spectrometer. I think they were pretty happy there at NASA when they worked out that acronym. So the infrared spectrometer is here. That's it there. And it's built onto the front of this aircraft, which is one that can go very high altitude, right up into the thin parts of the atmosphere, many kilometers above the Earth's surface. And it can sample the upper atmosphere, the stratosphere and the troposphere. So what it's got is a high-res infrared spectrometer. It's got 4-channel scanning tunable lasers, so absorption in the range of 3 and a bit to 8 microns, so through the near infrared and into the far infrared, can be studied. And multiple samples can be studied simultaneously, and then they can be deconvolved out of the infrared spectrum. And gases down at levels of subparts per billion can be detected. And the way that this is done is this neat little device here called a Harriot cell. So this actually says here it's an 80-meter path length. Well, the cell's not 80 meters long. This is actually about 1 meter. So the absorption's happening in there. We've got a cell of about 1 meter, but it's got some nice optics inside it. And so this is a little example, simplified ray diagram here, that the laser is bouncing backwards and forwards through this cell off these curved mirrors. And in the Harriot cell, it actually makes 40 passes up and back. So it effectively covers 80 meters. So that chamber is filled with gas from the upper atmosphere, and the laser passes through it 40 times up and back, so it covers 80 meters. It's like it's going through 80 meters worth of the atmosphere, so that some of that laser is absorbed and then detected at the other end, so that an infrared spectrum can be generated. Here's an approach which uses the entire atmosphere as the path length for doing gas analysis. It's called solar occultation, and yes, the word comes from the same origin as the occult. It means hidden or obscured, and hence the association of the occult being the hidden or dark or secret arts. In solar occultation, it's the sun that is obscured by whatever is in the path length between it and your observation point. So, for example, molecules in the atmosphere. So the sun is the source, and the detector is down at ground level, and as the sunlight passes through the atmosphere, some of it is absorbed, hence the sun is hidden, as it were, and then what passes through is detected and analysed. There is a really good research group at Wollongong that does this, and they have, up on the roof of their science buildings, they've got UV-vis spectrometers, FTIR spectrometers, and they routinely analyse and monitor for a whole range of atmospheric gases, these important CFCs. So we're still monitoring those to make sure that we don't increase these anti-ozone gases, plus of course all these other photochemical pollutants. An extreme version of solar occultation, which goes the whole way through the atmosphere at various depth profiles, like this, so imaging crossways through the atmosphere, can be done from a plane or a balloon, or if you're really fancy, it used to be done using the space shuttle. So the space shuttle would get around the world in a bit over an hour or so, and as it was orbiting, it would pass through a point where the space shuttle was out over here, and there was a good chunk of atmosphere between it and the sun. So it was effectively getting a sunrise or a sunset, and this would happen very quickly. There'd be about a 30-second opportunity to do a solar occultation measurement long ways or slice ways through the atmosphere. So some advantages and disadvantages of infrared for doing gas analysis. This last one is worth mentioning. It's no good for homodiatomic molecules. I'll leave you to work that one out. So can Raman spectroscopy be used for gases? Yes, it can. But as we saw in the previous video, Raman scattering is weak. Remember, most photons are scattered inelastically, so they don't change their energy. Only about 1 in a million or so photons are scattered elastically. So this is especially problematic for gas, where the molecules are sparse, so sensitivity is very low. You need hundreds of parts per million of your analyte really to be able to get a good Raman signal. But one advantage related to the previous slide is that homonuclear diatomics can be studied. So here's a couple of applications. On the left, we've got real-time monitoring of respiratory gases. So someone can be just hooked up to a spectrometer like that, and what they breathe in and out, that gas sample can be analysed in real time. Particularly useful, for example, during surgery. A more dramatic application is in monitoring rocket fuel. So H2, because it's a homonuclear diatomic, FTIR is no good. And you may recognize that picture. That's the very unfortunate Challenger space shuttle incident where it exploded not long after takeoff. And after this unfortunate Challenger explosion, NASA realized that they needed a fast and reliable sensor for detecting hydrogen leaks. That's their rocket fuel. Their requirements were they need a 2-second response. They want to be able to shut down and call off a launch within 2 seconds of a leak occurring. And they needed to be able to detect 200 parts per million by volume, they decided that was enough to constitute a leak and that launch should be aborted. And they also couldn't do any calibrations. It needed to be real time. And they ended up going with Raman. They ended up getting a Raman-based monitoring system for subsequent shuttle launches. So, can UV-Vis be used? Of course it can. Very useful in atmospheric work. Great, of course, for homonuclear diatomics. And we're going to have a quick look at a spectrophotometer that the Weather Bureau still uses to monitor ozone, and then a version of UV-Vis called differential optical absorption spectroscopy. So the Weather Bureau uses a Dobson spectrophotometer. 70 years old, and it works just fine. It's got a really high precision double monochromator, and it measures relative intensities of pairs of wavelengths. So it gets extra sensitivity by taking a ratiometric approach. So when looking for ozone, there's the Huggins ozone band. So this is a section of the ozone spectrum that has a name. And then another section is the Hartley-Chappis band in these different regions of the spectrum. And what the Dobson spectrophotometer does is it measures the absorption at one wavelength where the ozone absorbs and another where it doesn't. And it calculates the ratio and determines the amount of ozone from that. So it looks a bit like this. Because the signals are quite different and the dynamic range in UV-Vis is limited to, at most, really an order of magnitude. If you go from absorption of 0.1 through to 1, you've covered the whole range of fraction of light absorbed. Absorption values of less than 0.1, you only have a few percent of light absorbed, and greater than 1, you only have a few percent being transmitted. So that's pretty much the dynamic range. So the way the Dobson spectrophotometer works is it drops in what are called neutral density filters. So this is an ND filter, and that attenuates this wavelength where there is no absorption down to a level where it can be measured. So these signals now in a similar dynamic range can be measured by the detector. Then we know the attenuation factor from the ND filter. That factor is just applied to this channel and then the ratio determined from that. So differential optical absorption spectroscopy is very useful for environmental monitoring, particularly for pollutants and trace gases down at ground level. So where you have a good clear path length over many meters or even a kilometer or two, UV-Vis beam can be shone through the atmosphere to a detector and a UV-Vis measurement done that way. This is used a lot for ground level monitoring of photochemical pollutants. So when on a hot day you have a lot of car traffic producing photochemical, or producing exhaust which then reacts in sunlight to produce photochemical toxic gases. So all sorts of trace gases and nasty photochemical species can be detected using differential optical absorption spectroscopy. So here's a quick summary then of what you should know for infrared spectroscopy when applied to gas analysis. And here's a quick summary of the key points from applying Raman and UV-Vis to gas analysis. There we go. That's all for this video.